for dark matter. So my topic is to try to measure the liquid argon response for low energy nuclear recoils for the purpose of dark matter search. So before we embark on this journey, let me just take you on an outline of how this talk is organized. So first, I will introduce to you why we need dark matter. What do we know about dark matter so far? And let's imagine together, if we would like to build a detector to detect dark matter, how to go from simple kinematics to build this detector. But the main objective of this dissertation is to actually characterize the liquid argon response to low energy nuclear recoils from dark matter-like particles in an energy range from 2 to 10 keV. So basically, what we need to understand is how our detector responds when there is an energy deposit of really small energy caused by dark matter particle or a neutral particle, which will leave a signal similar to the one coming from dark matter. In order to do this, I will present the red experiment layout, the components, and the whole end-to-end data analysis that has been done mainly by me, leading to the quantification of the argon response in a detector-independent quantity. So when we need to provide a number that can be used in science, we need to have it in detector-independent quantities in order to be useful for the rest of the community. In this case, it's extracted electrons per nuclear recoil energy. So let's start this journey. Why dark matter? So we have a lot of evidence actually pointing that there is a component that we don't understand in the universe. However, I will just focus on two of the main evidence for dark matter. The cosmic microwave background is an radiation that came from some point in time in the universe evolution, which kind of told us about what was happening at that time. And what was happening at that time, there was a conflict between the photon pressure and the baryon plasma, dense plasma. So what was happening is that the baryon gravitational pulling was trying to pull the plasma inward, while the photon pressure is trying to push it outward. All of this under the influence of the curvature, the potential will that was provided by dark matter. So this cycle of contraction and expansion went on until at some point the photon decoupled at the very distinct temperatures that told us a lot about the dynamics of this dense plasma. So from this, we actually understood the ratio of dark matter with respect to other particles that we have. And another evidence is the bullet cluster, and it was the firing gun for the dark matter, which is an event that where two clusters actually merge. So they pass through each other. So we saw a clear segregation between two components, the stellar component, the one in red, the hot gas, and the gravitational center, which constitutes most of the mass of the cluster, and this one shown in blue. So as you can see in this moving picture, that should be moving. Okay. Not moving really, but anyway, it should be moving. So they go through each other. The gravitational effect is staying in the center, while all the it is passing through each other, while the red part is the one that is actually interacting in the center. So we know that dark matter is having most of the matter in the cluster, and it's not interacting from this. So here's the same picture in all in the visible range, X-ray, and gravitational lensing, and the gravitational lensing technique. So what do we know about dark matter so far? So as a particle, we understand that it has to be gravitationally interacting. Since we see the gravitational effect, it has to be stable particle since it actually stayed since the emission of the CMB until now. It has to be not hot because all the large structure of the universe that we see today cannot be done by a hot dark matter. It has to be non-baryonic, so it's not a particle that we don't know because we haven't seen these kind of interactions before. So what it can be actually anything. Basically, these constraints are not that, are actually that broad. So in terms of mass, it can go from 10 to the negative 21 up to 10 to 15. And it can go from a brimoidal black hole to ultralight particles that can be responsible for this effect. But until now, we are actually investigating what particle could be responsible of this. And so can be that we're using the ordinary matter, that's the 5% that we know of the universe, to understand the thing that we don't know, which is the 26% coming from the dark matter. So now let's imagine how to actually build a detector that is capable of detecting this kind of signal. So one of the detectors that are able to this is the dual phase TBC concept. So in order to understand this concept, I'm putting here a schematic from the Darkside 50 TBC, which is a dark matter experiment, where you can see here that the dark matter particle is coming in, interacting directly, giving an S1 primary scintillation that we call S1, and releasing some electrons that we have an electric field applied here that drift these electrons up to the gaseous phase up here, and it's producing another signal from the same event. And from these two signals, we can do 3D position reconstruction. So we can understand the XY position from the S2 light map. And we can understand from the difference in time between the two signals, the dips in our detector. This detector also provides a way to discriminate against gamma. So it has the neutron gamma discrimination. And we, from experience with this detector, we understood that we can reach the lowest energy sensitivity by focusing only on the S2 signal. So this is the ionization channel, and this was what I was working on. So what are we actually searching for? Dark matter. Okay, so which energy range, which mass range, because it's a huge mass range. So as you can see on the left figure, on all this green area is the area that was excluded by different experiments employing different technologies, and they excluded this green area. In the white area in the between above the dashed line is the area that we're still exploring, and below the dashed line is the area where signals coming from solar neutrino and atmospheric neutrinos will overwhelm the signal coming from our dark matter, at least with our technology. So we're not sure that our technology will be sensitive under this line. So we still have some white area, but in this white area, there is a left part, which is towards low mass, and there is a big, like a white part towards higher masses. So in the low mass case, we understand that we have a lot of points here, but just be until 6.7 keV. But before that, in energies below that, we don't know exactly which trend is happening in our detector response. So it can be anything from 7 to 12, okay, at 1 keV. So what we need to do is to have independent measurements in this region where we can actually limit the systematic uncertainties in this and increase our understanding and sensitivity to this energy range. So the data coming from this lines are these theoretical data, and with the Darkside 50 calibration data that was not closed by two-body kinematics. Okay, so now let's move to building this experiment. So this, not actually an experiment to catch dark matter, but it's expectedly an experiment to understand how a dark matter will interact in our detector. So we are putting a dark matter-like particle, in this case it's neutrons, and the californium source is the one producing neutrons, shooting them at the TBC inside the cryostat in the middle. And then any scattering neutron will be catched by two plastic scintillator arrays that are 1 meter along the line. So here we get the start time of flight from the barium fluoride, which is two detectors monitoring the californium source. So we catch the gamma coming out with the neutron from the californium source, knowing that the fission happened. And then we catch the neutron that scattered and reached in the plastic scintillator, and we take the stop time. Here we have a start and stop, and we can calculate the time of flight that it took from this between these two detectors while actually leaving a trace inside the TBC. So we took the TBC in slave mode, and we collected this data. But simple kinematics are not that simple. So you need to actually go through a lot of equations to go through understanding how much event rate you will actually receive in the I'm not sure what's happening. Sorry? You want something?
Yeah, because
Yeah, okay. I have no clue. But anyway, it's just referring to these X, Y, and Z, explaining them in the equation. But anyway, so the equation to calculate the event rate within the TBC is having a lot of input coming from nuclear particle physics, coming from astrophysics, and from our understanding of the detector itself. So we put all these things together, and we need to understand how many events we will collect in our detector based on these equations. More details, of course, are in my thesis, where I follow the full derivation of this equation. So the experimental components, as I said, the californium source is hosted inside a shield of foreign-loaded iron to, or of course, protect from radioactivity. The shield has a collimator of 2 degrees that collimate the neutrons beam coming out of the source, and it makes sure that this 2 degree is having even illumination of the TBC, which is placed 1 meter below that line. And then in the vicinity to the californium source, there is the 2 barium fluoride detectors that's getting the start of the signal. So they have to be a fast scintillator detector that can stand the event rate without pileup. And that's what was used here. The barium fluoride detectors with 0.8 nanosecond decay constant, and they provided the start of the time of flight measurement. And then the neutron spectrometer, which is 2 arrays of 3x3 plastic scintillators, 1 inch diameter each. And they have time resolution of less than 1 nanosecond, and they provide a stop time of that time of flight measurement, and they feature also neutron gamma discrimination, so we can understand whether what we catch is a neutron or a gamma. The main component is the TBC, which of course we're acquiring in slave mode. However, our detector, this is meant for calibration. Idea, same concept of the same detector that can be used for dark matter. So it's 5 by 5 by 6 centimeters coated with TBB2 in order silicon photon runs that were taken regularly during the whole data taking campaign. We calculated the light yield, and there you can read more about the performance of the TBC in this paper. Then in order to actually analyze the data coming from this detector, we needed to build a software. So my work was building a modular Python software that has 1 module dealing with each step of the reconstruction, or let's not use jargon, of understanding the physics quantities out of the data that we collected. So as you can see, these are the terminal while reconstructing 1 event. And the calibration for the lasers, so we can go from raw waveform until we find the hits on each event, on each channel. Channel is a detector, whether it's a plastic scintillator or SEPM, or in this case is a SEPM, but anyway. And here we understand how much of the charge the detector unit equal how much kilo electron volts. So to like kind of connected to physics. And we can also produce these kind of figures that monitor all the detectors at the same time. So we can do this exact figure along the data taking campaign. So we make sure that the performance of our detectors didn't deteriorate along the data taking campaign. So what we took is data coming from January 10th till March 16th. We had these data were collected on a trigger that requires only 1 barium fluoride and 1 plastic scintillator to see the signal within 200 nanosecond of time. That allows a 1 mega electron volt neutron to travel from the source to the plastic scintillator. The TBC acquired in slave mode, as we said, since the lowest energy sensitivity of this detector comes on focusing only on S2. So we cannot trigger on S1. So we acquired it in slave mode, but we are looking for once we have a coincidence between the barium fluoride and the plastic scintillator, we look at any trace left in the TBC. And then, of course, the coincidence events that we caught was about 10 million, 60% of the spontaneous fission events. Weekly calibration was done using laser and known sources to like correct for non-homogeneities in the TBC performance. And to verify this reconstruction algorithm, we went with a Monte Carlo simulation that pipeline as the real data and produce the same plots, so we can make sure what we are doing is exactly what we intend to do. So what we actually did is a lot of things. I'll go through them briefly. So we have a lot of detectors, so they weren't synchronized at first. We tried to synchronize them in time by using the gammas that directly went from the two taggers, the barium fluoride and the plastic scintillators, and we evaluated the resolution of our time measurement sensitivity. This is on the two detectors for the barium fluoride. Also, we used another parameter to choose our select events. So it was the F prompt, which is the integration of the first part of the first 100 nanoseconds of the pulse over the whole integration of the pulse. And it tells us that there are two populations of particle types. The first one here is the gamma, that has the gamma flash that has a higher F prompt but lower time of flight, and the neutron bulb population that is having a longer time of flight. So we select that gamma flash here, then we look at the energy parameter space, the F prompt versus energy. We draw this parameter space with and without this cut on the time of flight, and then we can see the gamma distribution. And from this gamma distribution, we can okay, it's a bit slow. This gamma distribution, we can require that only 0.1% of contamination goes into our final sample in this thing. So this exponential curve was modeled in order to allow 0.1% of contamination in the final sample. Okay. At the end, we reached the event selection and analysis, so we were able to individually select the neutron and gammas, as you can see here, and we were able to reproduce the Californium spectrum, as you can see here. We had a 28 neutron per hour. Most of the events were dominated by gammas, and which were accidentals and which were expected by the Monte Carlo. The time of flight resolution is 0.7 nanosecond, and we did a deconvolution of the symptom response, and our pulse finder was able to fully efficiently detect any pulse of S1 above 25 PE and any S2 above 4 electrons. And there are more selection cuts that I can go through, but it's gone through in details in in my thesis. And you can see that here, after applying just the time of flight and F prompt cut up there on the top left corner, blue. And then we can apply one by one the quality cuts to cancel any events that are not accidentals. So they are not actually a true coincidence between the three detectors. And we can reach the final sample of this neutrons that we have here in red in the bottom right corner. So to build from this QY distribution, we take energy slices, recoil energy slices, and for each slice, we evaluate the median and the error on mean on this thing. It can be, of course, done in a more appropriate way of doing fitting with a Gaussian plus a background. However, for just the time constraint, I wanted to do the whole by blind. So I just gave an idea of what estimates we can get. And it's not that far from the true results. So you can see here that we have for each pen, these are the 4 lower energy bends. And you can also calculate the systematic uncertainties, which I went through into the thesis. However, I will not going to go through into here, and it can be done, of course, in a more appropriate way using a Monte Carlo simulation, which is currently done. But here is just to get an idea about the uncertainties that we have. So at the end, we reached that we have 800 events past all quality cuts out of the 2,300 neutrons that were catched without a trace in the TBC. The nuclear recoil energy was calculated on an event-by-event basis, and we assume we say that uncertainty on is plus or minus 5%. Most of the S1 plus S2 events are outliers, so they're coming from multiple scattering of the neutrons inside the TBC. So they are not that important, as we mentioned. And the S2 actually provides the lowest energy sensitivity, and we have points down to 1 or 2 keV. We compared this with the data coming from DarkSide 50 and Joshi, and using the preliminary value of G2, which was evaluated by doing a cross calibration with DarkSide 50 data. And in conclusion, we actually managed to characterize the liquid argon response to low energy nuclear recoils. From dark matter-like particles, which are in this case neutrons, we managed to have points below the lowest measured points by Joshi, which is at 6.7 here, the one in teal. And we have all these red points down to 2 keV or 1 keV. There's a lot of things that can be done to enhance or refine this analysis I mentioned them in the conclusion, and they are currently under investigation. And they're not limited to just this list, but this is just some of the things that we can work more on, like the timing accuracy of the barium fluoride, since one of the barium fluoride wasn't acting nicely, the calibration of the plastic scintillator, the refining of the analysis to understand the sebum noise much more, because one of the sebums were getting more dark count rate. We can improve the event selection through more quality cuts that we can apply. We can optimize the XY reconstruction and correct the S2 value. And finally, we can calculate the G2 factor, which is the gain factor, the ionization gain factor, directly from the red data, instead of doing the cross collaboration with DarkSide 50, which I needed to do to get the value to get to the final curve, that is the QY value on the y-axis, instead of the number of electrons, which is a detector-dependent quantity. So thank you. And the future is dark, but dark matters. Thank you.
Thank you very much. Well, there should be some light somewhere there. Okay, thank you. So we know what the dissertation is about. We know the supervisor's opinion. Now, time for the more critical part of the defense, which is the reviewer's report. And I would ask the reviewers in alphabetical order. So please, Professor Zakhary, present your report. And like I said, you may present your report in full or in parts. You can interact with the candidate or just present a report. It's up to you.
Okay, so can I start? Thank you very much. So I'm going to read my report. The PhD thesis of Zakhary.
It's working. We don't hear. Yeah, just click closer. Sorry.
Okay, so the PhD thesis of Paul Zakhary has 112 pages, including a bibliography and appendices. The main contents of the thesis are a series of analyses conducted at RED experiment to understand the liquid argon's response to low energy nuclear recoils within the 2 to 10 keV range. In this kinematic range, an isolated ionization signal called the S2 or S2 only signal is important. The analysis performed by the author aimed to estimate the ionization yield, which is an important detector-independent parameter for the S2 signal as a function of the nuclear recoil energy. These analyses have great scientific value since a good understanding of liquid argon's response to low energy nuclear recoils is crucial for liquid argon-based direct dark matter detection experiments with a dark matter mass range around 1 to 5 GeV. In fact, the current world-based limit on the spin-independent dark matter nucleon cross-section in this mass range is obtained by the DarkSide 50 experiment, exploiting the S2 only signal. A better understanding of this signature as well as the background and uncertainties, has the potential to improve the dark matter detection sensitivity to the dark side experiment further.
Line.
The thesis consists of 5 chapters, bibliography, and 2 appendices. Chapter 1 provides an overview of dark matter, beginning with its scientific history and so on. So the later is just summary part of the report. So I just skip to the important part. Overall, the thesis of Paul Zakhary is well written and mostly clear. The thesis presents the motivation for the dark matter search, liquid argon's response to low energy nuclear recoils, the scintillation and ionization signatures in the time projection chamber, and details of the RED experiment, and author's analysis to determine the ionization yield with the RED data. Although the final result presented in figure 4.17 is not yet complete, as the G2 factor remains preliminary, it presents a significant step forward in improving the sensitivity of the dark side experiment to dark matter candidates with masses in the range of 1 to 5 GeV. The presented results are original and hold significant scientific value and impact. While the quality of the thesis meets the standard, there are a number of places where the thesis can be improved. First, the thesis lacks the proper introduction. The first chapter of the thesis should be devoted to the overall introduction, describing the scientific background and motivation for the main experiment and analysis. The presented mathematical equations are occasionally imprecise. For example, sigma SD in the bottom equation in 1.38 cannot be the same sigma SD defined above. Equation 4.6 and 4.8 are not properly written. On page 9, it should be tau larger than 10 to the 17 seconds rather than tau equal to 10 to the 70 seconds. Additionally, the logical steps are sometimes difficult to follow, and some technical terms are used without being defined. For example, on page 3, omega and lambda CDM models are not defined. And also, it is unclear what the author wants to say with equation 10.1.10, where the left-hand side and right-hand side represents dark matter cross-section in different theories. And the author claims that equation 1.15 is obtained by solving equation 1.14, but this cannot be done without specifying phi of r or postulating some relation between phi of r and rho of r. And in section 1.5.3, the spin-independent and dependent cross-sections are not clearly defined. In section 3.4.2, in section 4.2, Ke initial energy is relativistic, while the out state energy is non-relativistic, and there is no explanation why. Apart from those points, the contents of the thesis are understandable, and the results have significant scientific value. In addition to the analysis, the author contributed to the RED experiment by assembling and adjusting hardware devices and performing calibrations. Together, it shows the author's firm understanding of the experiment and capability of perform scientific works independently. Summing up, I consider the doctoral thesis of Paul Zakhary to be valuable contribution and to meet the criteria prescribed by the law for doctoral dissertation. Therefore, I request that this dissertation be admitted to a public defense.
Thank you very much. Thank you. So I think we now proceed to the second reviewer's report. Professor Świderski, welcome. And with the answers and the discussion we can leave after the presentation of the reports. Yeah.
Thank you. So this is my the review report of the thesis by Paul Zakhary. The thesis titled "Measurement of Nuclear Recoils in Liquid Argon for Dark Matter Searches." And the thesis was prepared in the Particle Astrophysics and Technology Center at the Nicolaus Copernicus Astronomical Center of the Polish Academy of Sciences. The dissertation contains 128 pages with 112 pages of main body preceded by 16 pages comprising the title page. The dissertation touches the very important problem of characterizing the detector response, the detector that might be potentially that might be used for detection of potential candidates for dark matter, and it characterizes the author characterizes the response in the region of interest for potential dark matter detection. Then I just go briefly through the contents of the thesis. So in chapter 1, the author describes the cosmology models incorporating existence of dark matter as necessary component to explain the evolution of universe. The author also presents the detection scenarios indicating registration of nuclear recoils from WIMP's elastic scattering as the source of the signal that can be used for proving the existence of dark matter in that form. Chapter 2 contains description of operation principles of noble gas detectors based on argon. The author presents the concept of the dual phase time projection chamber containing argon in liquid form and in gaseous form is also described. In chapter 3, the author depicts the calibration procedure for measurement of neutron recoils energy by electroluminescence signals as the method for quantitative evaluation of liquid argon TPC performance. And in chapter 4, the author provides the description of data analysis performed within the scope of the PhD thesis. And what is worth mentioning that this analysis is presented in much detail. The author also discusses thoroughly the factors influencing the neutron recoils energy resolution, providing quantitative evaluation of uncertainty contributions. And finally, ionization yield is calculated from recorded data. Conclusions and prospects are presented in chapter 5. So the author recalls the achievement of the dissertation goal, namely the determination of ionization yield for low energy nuclear recoils in the energy range between 2 keV and 10 keV. What is important is subsequently he depicts a list of modifications, extensions, and improvements to the experimental procedure that should result in achieving more precise and reliable result, and it's very important for a continuation of these experiments. And the provided results gives an opportunity to compare the data with theoretical predictions. Previously, the only source of ionization yield estimation at such low energies. So then next, there are some general remarks and my comments to minor mistakes or maybe inconsistencies in the text that does not influence in large extent the content of the thesis, and I maybe just present some major comments to the text. So the author says that the source used was 26 kilobecquerel activity, and it is inconsistent with the yield that he reports in the thesis. So I asked about to comment this. Then in the equation 3.1, he defines the recoil energy as a function of scattering angle in center of mass framework, whether in the appendix provides a derivation employing laboratory angle, and is still not reaching the formula for recoil energy, though it is not far from achieving the final result. The reader should be informed about approximations used here, I think. The procedure for evaluation of photoelectron yield is not perfectly clear to me. Maybe some word was omitted in one of the sentences I mentioned. And it also would be valuable to have a comment why integrating window width was chosen 4 microseconds. And I think it was a very valuable result to have the neutron with high quality clearness. The introduction to the topic may serve as a good review of currently studied models of dark matter. And I emphasize the value, the detailed description of the experimental setup and calibration procedure. The result obtained by the author is of great significance for preparing the detection and for preparation of the detection setup to the main goal, to the experimental campaign. And I think that the author revealed that he has a profound knowledge and experience, his profound knowledge of the topic as he presented the analysis and the discussion. In summary, I consider the doctoral thesis of Paul Zakhary to be a valuable contribution to the field of dark matter research and to meet the criteria prescribed by the law for a doctoral dissertation. Therefore, I request that this dissertation be admitted to a public defense. Thank you.
Thank you very much. Thank you. So now the report by Professor Wrońska.
Why don't you take a seat?
Okay, do we?
So the aim of my assessment of Paul Zakhary's thesis was to determine whether the dissertation fulfills the prerequisites for the conferment of a doctoral degree, and these are 3 of them. The dissertation constitutes the original solution to a scientific problem. It demonstrates the candidate's general theoretical knowledge in a given scientific discipline, and it demonstrates the candidate's ability to independently conduct scientific work. So in my report, I referred to those points. I will not bore you with repeating again what the thesis is about or how it is structured. It has been said by my colleagues. So let me just address those 3 points and the criticism then. So the content of the thesis shows that the author has broad knowledge on dark matter, both from the theoretical and experimental side. The red experiment described required from Mr. Zakhary to develop expert skills in hardware as well as in data analysis. Although in the latter aspect, he certainly took advantage of the existing data analysis codes from the collaboration, but as we heard, not only. This shows that the requirements 2 and 3 of the list, which I just read out, have been met. The main result of the red experiment, which is the determination of the argon ionization yield in the detector-independent units, gives impressive results that extend the scarce data delivered by other experiments for the nuclear recoil energies between 2 and 10 keV. The analysis is preceded by careful calibration of all involved detectors. I enjoyed in particular a very clear exemplary description of the noise characterization of silicon photomultipliers in section 361. The other project described in Appendix B, although it was concluded with only indirect evidence of argon-37 production from the presence of potassium-42, paves the way to further experimental studies on the topic. Notably, the project and its outcome have been published as an article in the Journal of Instrumentation, which is signed solely by Mr. Zakhary. And it shows, in my opinion, that he was the driving force of this research. And this confirms, along with the main doctoral project, that the requirement 1 has been fulfilled as well. Additionally, Mr. Zakhary co-authored 5 other articles, including 1 preprint, some of them as a member of collaborations, other in smaller groups, but this all in total shows that he integrated well in the community and was able to work together with other researchers. So proves his ability of teamwork. The author contributions to the thesis content are very clearly stated. I liked it, that it's absolutely clear what he did, and there is no doubt that his contribution is significant to this project. Having listed the merits of Mr. Zakhary's dissertation, I would also like to pose several questions, actually more than several, that occurred to me when reading the thesis, and which indicate that there are some shortcomings or mistakes contained in the thesis. I divided them into 2 categories, major and minor. I will not touch the minor one, as the major list is pretty long in itself. So I will restrict myself to the main points from the major issues, okay? So it starts with the introduction, where in section 1.1, the reason for introducing the lambda factor in Einstein's equations was stated incorrectly. So the history is different. Maybe you can explain what you learned about it. Then in section 2.3.1, first paragraph describing formula 2.4. From the description, the left-hand side is the energy loss, which is the integral quantity, while the right-hand side contains differential quantity. So even the units don't match. I would like to hear a comment on that. On page 31, the author discusses different values of the alpha parameter in the literature, and there is quite some range spanned by the literature values, and the author leaves us without any comment on this huge discrepancy. There are also such details like in figure 3.1, where this same quantity is presented in 2 different units, and even though the units scale by a factor of 10 to 24, the numbers in the axes are different. So there is something wrong with the recalculation, it seems. Finally, there is quite a number of places where I was missing some more carefulness in the statistical analysis of the data, namely, for example, the figure 3.7. Which calls for a more elaborated fit in a number of places. You just fit it very Gaussian, while the peaks were visibly located on some non-uniform background. So that should have been modeled better. There were also uncertainties missing of the fit parameters, or stated with excessive precision when calculating the uncertainties of functional parameters. You omitted correlation between parameters fitted. So these were such shortcomings that I disliked somewhat. There is a statement about the energy resolution of the barium fluoride detectors without specifying at which energy it was determined, and as it was determined based on 4 spectral lines, I think, it's not clear where the and we know that the energy resolution is an energy dependent quantity, so this is unclear. In figure 4.3, the data, I'm asking if the data are plotted for a single psi channel, because if so, then given the if not, then the scatter of the peak location for different psi's before the correction and after the correction, I would expect the scatter to be reduced, the peak to be narrower, which is not really observed. One of the major points I had troubles with was why the G2 factor has not been determined based solely on the red data, if the steps to achieve that were all presented in the thesis. And maybe the last one, high purity germanium measurement is susceptible to some uncertainties. This was the statement which we find in the thesis. So I was lacking the explanation what kind of uncertainties were meant by that, because this type of detectors is routinely used for high precision spectroscopic measurements and activity determination. So I was not sure what was meant by that. Although the level of English is overall very good, the punctuation and capitalization are a somewhat weaker side, plus some other so I'm looking forward to hear the answer to my to my criticism. But yeah, all of the criticism that I just listed, this does not really change my positive assessment of the dissertation and the overall outcome of the project, both the main part and the side project with Argon 37 production. And summing up, I consider the thesis to be a valuable contribution to the field of dark matter search and to meet both the substantive and formal criteria prescribed by the law for a doctoral dissertation. So I request that this dissertation be admitted to a public defense.
Thank you very much. Thank you. Well, a discovery can only be called a scientific discovery if it is verified, criticized, and goes through the defense. So, you know, this is the necessary step. Okay, perfect. So we've all the critical and positive remarks. So your turn, and of course it's an interactive part already if you want to engage into discussion.
Okay. First, I would like to thank you for reading my thesis, taking the time and reading it and going thoroughly through it and providing the comments. I really appreciate it. I will actually implement on most of the reviews that was mentioning some minor mistakes. I will implement them, of course. Dzień
dobry, pani mówi Marta Borowiec. Ja kontaktowałam się z państwem 2 dni temu, o ile pamiętam, rozmawiałam z panią dyrektor.
Perfect, thank you. Okay. So, thank you. I would like to actually reply to your comments, and if you have any comments on my replies, of course, feel free to interrupt me. So I put all the comments each in one slide, so we can go through them one by one. I had a bit of different but okay, Professor Alexander. So in section 1.1, the reason for introducing the lambda factor was incorrect. It was introduced by Einstein long before the observation of the expansion of the universe. And this is true. Of course, I understand the history. I was just trying to focus more on the end result more than the just saying what happened in the historical way of discovery. So, of course, at first, Einstein like just put the cosmological constant as a constant, and he didn't actually just to fix the universe as it is. But then he, if like a lot of other measurements, supported that there is actually the dark energy factor, and then in history it came down to that this lambda refers to the dark energy contribution in the equation. So I appreciate the gesture, but this is just for historical point of view. If you would like to know more about it, it's covered a bit in a lot of the textbooks. So yes, the lambda is the cosmological constant. It was first introduced historically for the wrong reason, and now it's accepted to be used to be the for showing the contribution of dark energy to the equations. In comment 2, it's not supported with a reference, and the symbol omega with an additional subscript 0 are not explained. Yes, maybe I would have mentioned it in a different way, but in this dissertation, I'm trying to follow the convention of just defining the first time in each chapter, where I go through a different symbol. So, I think I explained the subscript in equation 1.4 and 1.5. This is equation 1.6 that has the issue. So the omega is explained as the last statement. Here, omega is the summation of all the omegas coming from the different components, and they say the energy density mainly. So it's the energy density, the omega, and it's the I refers to either baryonic matter, dark matter, radiation, or dark energy contribution. So this is the one. The subscript 0 signifies the current value of any time-dependent parameter. So if I'm saying H0, this means the Hubble constant and this time. So I just explained it for H0, but I think the 0, I used it also for the omega. So omega 0 also makes the same thing. So the current value of the time-dependent component parameter. Comments 3 and 4. In the first paragraph, the electric moment and of the neutron without giving the reference are particles types relevant in the axion search as well. Yes. Okay. So in the introduction chapter, I was mainly introducing things that was settled way before me in science. So I didn't need to kind of make sure that every statement having the reference, even though I should have. I was just if I'm talking about in one paragraph about one topic, I mention in the first sentence that this is the reference where it's taking from, and then I complete the same paragraph talking from the same reference until I move to a different topic where I mention a different reference. So in this case, maybe I would have made it more clear by putting the reference on front of the important information if I'm saying something scientific or details. So whether some other particles are relevant to the axion search, I'm not that expert in the topic for the axion search. However, I believe that the electric dipole moment is a factor that is affecting this. I think for now, this is the only thing that is contributing. However, I'm not quite sure, but there's a lot of other scientists who are focusing on the axion search.
First of all, you teased me with this statement that the EDM of the neutron is of significance here because I work on searching for EDMs of charged hadrons. That's why I asked this provocative question.
Okay. Okay, I'm sorry. Yeah, but yeah. Okay, so I'm sorry. I might need to discuss more with you after. Okay, so in section 1.43, the author discusses Sorella and Trias. I'm missing the reference. Also, the reference I'm sorry about. I will make sure that I will include the reference directly in front of each statement. So here are, yes, this is true. I did a mistake in this equation. I put that the left-hand side is, I kind of said that the nu and v are the energy lost per unit distance, and with the way I defined it. However, I put on the left-hand side an integral quantity. So this is not accurately correct. It should be either both differential sides or both integral sides. So it's my mistake. On page 51, and reconstructed the waveform by utilizing a prolonged charge integration. So yeah, the word reconstruction, I understand it's a jargon. Maybe it doesn't make any sense to you why we reconstruct waveforms. Okay, remove this word. It's just a way of we use this word when we say to take the physics quantities out of raw waveform. So in order to calculate the integration under the pulse, in order to know the time at which the pulse had the highest amplitude, the start of the pulse, the end of the pulse, these kind of things. So in order to take these physics variables out of the waveform, we call this process reconstruction. So figure for B4, it's in the appendix. How was the bending adjusted? I would expect better fit for the coarser bending. Yes. Like a bigger bending would have less, would either have the same information or less. So it cannot have more information. So it was just for visually see the peak as going up and down. If we just chose to put the content of each pen in two pens. So if the peak will show like this super narrow, I'm just making it a bit wider for visual, making sure that it's visually a peak. That's it. So it's not affecting the calculation of the mean value or the error on mean. Comment 6, equation 2.6, the interpretation of parameters K and E is not stated. For K, it appears later in the text. Yes, I actually aim to highlight the role of these parameters in the equation more than the naming of what they stand for, because actually the naming is quite complicated once you hear it. A small e indicates nuclear stopping power, efficiently transferring energy to nuclear motion, while E signifies the increasing electronic stopping power, leading to the energy lost through the electron excitation and ionization. So sounds a bit scientific, but it's not giving you what exactly they're doing.